We're going to continue to take a look at applications of integrals, and in particular, we're going to take a look at volumes of revolution. Now, at the end of yesterday's lesson, we did an extension on a problem in which we did look at a volume of revolution, and then looking at what happens if squares are formed from your area. Well, here's some objects which are basically volumes of revolution. Here's part of an axle, here's a funnel, here's a pill, here's a bottle, here's a piston. Basically, it's the same shape, just revolved around an axis, forming a volume of revolution. Now, based on what we talked about yesterday, hopefully this will help you here, where you see this, and it's being revolved around your axes right here, forms this big disk. And the volume of a disk is just the area of your circle times your thickness. And that's what we're saying right here. Well, if we would take a slightly more interesting shape, which would be this blue shaded region right here, and revolve it around your horizontal axis here, we would get this blue region here in the middle. And well, you might be wondering, where is this kind of tan ring right here? Well, there's a little bit of this tan rectangle sticking up and above your shape right here. This little triangle piece right here is, when it's revolved around, that tan ring. So when you revolve this shape right here around the x-axis, you get this shape. Now, if you did lots of, or several rectangles along here, it would look like this. And as you would try to get a more accurate answer, you would do thinner rectangles, which would be thinner discs, which would be more discs, would give you a more accurate answer. And that's where the integration comes into play. Now, we had said your volume is your pi times your radius squared, because that's the area of a circle, times your thickness. Well, in the context of what we're doing, we're dealing with pi, your radius squared, your thickness is your dx, and since we're adding all those together, instead of going back and doing Riemann sums, it's just your integral from a to b. If you are revolving around a horizontal axis, it's this formula. If you're revolving around a vertical axis, it's this formula. The only difference is here you're integrating with respect to y, which means you need to have y's in your function. So we need to go ahead and integrate or revolve this shape right here around our x-axis. Now, this is not a perfect shape of what we're looking at, but hopefully it'll help you visualize it. Our shape is similar, and now this is being revolved basically around your x-axis, and now you're able to see kind of the shape that's formed. And we're looking for the volume of that shape. Well, we need to use this formula here. We are going to put our pi down. It says all the way up to x being 4, and you'll notice that would be right here, and we're starting out at 0. So we're going from 0 to 4. It says take your function, which is just root x, square it, dx. Well, root x squared is x. Now all we do is you integrate that, and then all you have to do is evaluate that, so you end up getting 8 pi units cubed. Here we have the root of sine of x. When you look at your graph, it's this shape over here. And we're revolving this once again around the x-axis. So we're going to start off with this same basic formula. We're going to put the pi down. You'll notice our shape goes from 0 all the way over to pi. And it says your function squared. So I have my function I need to put in there and then square it. My function, once again, is my root of sine. Well, the root of sine all squared is just sine. Integrating that is negative cosine. Then you need to evaluate that. And so you just get 2 pi for this football shape right here. Volume formed by this. Well, that is their shape over here is given to us here. There's our parabola. Here's our y equals 1 line, and we're revolving it around that. Well, that shape then is given to you down here to help you visualize what's going on. Well, we need to go ahead and take a look at our radius. Your radius is basically just this right here. That red distance is your radius, which in essence is the top function, which is our parabola, minus our bottom function, which is just our horizontal line, which does reduce down to 1 minus an x squared. Well, we're going to have to use our formula then. We're going to integrate from a negative 1 all the way to a positive 1. Our function squared, once again, that was top minus bottom function, which reduced down to this, all squared. Then all you're going to want to do is just FOIL that out. 1 minus x squared times 1 minus x squared. Just integrate that then. Plug in your 1, subtract what you get when you plug in negative 1, and you end up with 16 pi over 15. Well, we now need to take a look at the volume of another shape, which is a washer. If you would take this shape right here, which is a rectangle up in midair kind of, revolve it around this, you really get a washer. Well, to figure out the volume of this washer, it's really the area of the whole big disk, which is this first part, minus the, or I said area, volume of the whole big disk, minus the inner disk. We're not looking for that inner disk. And well, that's this one here. Big R's for your big outer radius, small r's for your inner radius. This is going to be what you're going to use for your volume of revolutions when you have a middle part missing. So we need to go ahead and take this shape here, revolve it around the x-axis. When we revolve it around the x-axis, we end up getting this shape right here. Kind of a bowl with kind of a small bottom on the inside, but then hollowed out here. That's what we need to go ahead and end up with. And we need to figure out our volume of that based on our initial two functions up here. Well, you'll notice our functions cross at the origin. They also cross at the point 1, 1. Our top function here is the root function. Our bottom function is our parabola here. And so then we're going to start out with our basic formula of pi, integrating once again from 0 to 1, of our top function, which is the root x, all squared, minus our bottom function, which is x squared, all squared, because it says to square those. We square each one, then we do our integration, and then we evaluate it.